I'm going to be asking sort of a relatively simple question this morning, and that's just whose water is it? We wanted to look at how we can sort of effectively divvy up responsibility for different sources of flooding. And then we wanted to see how best we could do this using the Innovyze software itself. So we were thinking, can we use a built-in function of InfoWorks to aid the identification of flood sources? So we wanted to be able to look at differentiating between pluvial, fluvial, and wastewater flooding. And then how can we actually quantify those individual components? So this is quite a recent example. This is the boat in Ironbridge. I'm sure you might be seeing more photos of the flooding from the past couple of weeks. But this is obviously something we can see. Most people, regardless of their background, will be able to look at this photo and say, oh, that looks like river flooding to me. And you know, it's a lot more clear when it's an extreme event. We've got one source. And then a different project I previously worked on back in November is we've got an external-internal flooding of a customer during heavy rainfall. And you can see from this photo here, this is taken by the customer, I believe, that the entire road is flooded, the property is flooded, and that's then become internal flooding. The water company went out on site, and we can see that there's a river overtopping into the road, and you start to think, well, this is clearly a river, fluvial-based flooding. But then the customer is adamant that flooding originated from the foul water sewer in the middle of the road. Obviously, looking at that flooding, that's not the only source. So now we have to, look at a combination of the three potential sources. So we wanted to use the water quality modeling, and we wanted to use a tracker in the wastewater system. So we wanted to effectively use dye testing, how you go out to a manhole, put some dye in, see where that comes out eventually, in your down system. So we looked at using dissolved pollutants as a dummy tracker with the water quality modeling functions, and we wanted to aim to set a baseline level of pollutant within the foul combined network to start off with. So we've got our 1D network, and first off, we need to go into model parameters, and we need to start setting up water quality and sediment parameters to sort of be able to use the functions that we rarely do for wastewater flooding. So we get, our drop down, go straight to decaying pollutant parameters. This is something we picked on quite early on, that in order to set a constant baseline level of pollutant within the system, if it's not constantly decaying. So we go into that, and we need to set our decay types for our pollutant trackers that we're using to none. And that's quite an important step into setting up our baseline conditions for the model. We're only interested in dissolved pollutants PL1 and PL2 for now, because we're not actually interested in sort of setting a realistic amount of the dissolved pollutants in the system. That's not what we're using the modeling for. So we just use PL1, PL2 as our dummy trackers. Next up, we need to then set our pollutants up in our wastewater profile editor, and we are only setting up PL1 for now because we're only looking at a foul combined wastewater system, and we just want to be able to get a feel for how we can actually use this for this step. So we're using PL1 as our wastewater flows, and we set a concentration at 10,000 milligrams per liter, and that is, you can just about see it, this section here. It's important to note that that is just an arbitrary value that we've used. Like I said, we're not actually looking to see a realistic amount of concentration. We just want a solid number that we can be able to track throughout our system. So we set up our wastewater profiles for each of the profiles that the model's using. We've set our PL1 at 10,000, and now we need to set up a run. So we've got a normal run group here. You've got your wastewater profiles in there. We've got a model. We need to set up a dry weather flow simulation effectively to see how the model works at first. But we need to make sure that we tick the use QM and we need to set up our QM parameters. So when you open up QM parameters, we want to be sure that we're using our dissolved pollutants for PL1 and PL1 only for now. The more you tick, the more simulation processing the model has to do, sort of analyzing each one of those. So we're not interested for any right now. We're just going to look at PL1, and we're not interested in sediment fractions at all. So disregard that. Importantly, we've got the QM multiplier, which is effectively how often the water quality model is calculated in comparison to your normal time step. So if you've got your time step at 60 and 5, using a QM multiplier of 5 will then, every fifth of those, it will calculate. So it's similar to how if you want a sort of a finer definition, you'd use a lower time step. We've settled for 5. It's a range between 0 and 10. We find 5 was the best to get a good representation of the changes in concentration without increasing unduly the amount of simulation time that's needed. So this is our 1D network, and this is just a dry weather flow simulation throughout the system. It's a simple network. We've got a couple of branches coming in. We've got a CSO at the top of the system, and at the bottom of the system even, at the top of the page. And then we've got a sort of outfall out of the system. So we just want to look at flows going through. So load our simulation in, and we want to graph our dissolved pollutants for PL1. And this concentration graph here is just showing how the concentration builds up in the system. And interestingly enough, this is quite a small network, but it's still taking about 6 hours to create a stable concentration of 10 kilograms per meters cubed. And this is quite a typical Innovyze function they like to throw in. They like to change the units every now and then between different graphs and different entry points. So we previously set up at 10,000 milligrams per liter. In our graphs, we're now using kilograms per meters cubed. I'm sure we can change this in our tools for native units and things like that. But it's just important to make sure you're always keeping a constant note of which units you're using at that time. So we've used this sim as our initial state. So it's taken 6 hours, but flows through the system have reached a point where we've now got a steady state of 10. So if we now use this as our initial state file, our flows should start at 10 rather than having this build up concentration. So now when we start to look at a storm event, which we can see here, we'll see the changes of concentration in the network from the input of what we are classing as clean surface water runoff, effectively. So we've got our surface water runoff coming into the system, and we're treating that as clean. We're not assigning any pollutants or any sort of sediment runoff going in right now. And it just acts as a simple dilution of our wastewater. So if we first look at the graphs on the left, we've got our concentration on the top graph and then flows at the bottom. And this is flow over the CSO itself. So we're seeing a very characteristic first flush of pollutant coming over the CSO, which is the start of our spill here. That then starts dropping down, and then we get sort of a second flush through as our rainfall event is stopped and we get more wastewater coming back through. And then our second set of graphs, we've got our flow leaving the system, starting off at 10 kilograms per liter, 10 kilograms per meters cubed, instantly dropping down where we're getting this influx of clean water, and we're dropping down to a very low concentration. At that point, that's then building back up. But interestingly, we're then getting a spike up to about sort of 15, 16 kilograms per meters cubed, which we're not too sure about why it's doing this, as the wastewater is effectively becoming more concentrated than what we're putting it in at. So that doesn't really make sense to us at the minute. So if anyone's got any ideas about why it's doing that in the software, please let us know, because I'd love to know. So we've got our 1D model set up. We've proved, yes, we can use our water quality as a tracker, and we've just got a simple setup where we're just using PL1 and flows flow through. We can track it going over CSOs. We can track flooding, things like that. So we wanted to try and build up the complexity and bring in additional sources. So this is what I've mentioned previously, PL2. We're now going to use PL2 to track our fluvial flows. So we've got a separate model here. We've got the integrated 1D, 2D model, and we've got our river modeled as well. And to do our river modeling, we've got inflow hydrographs at 2 points, start of one watercourse here, start of another here, and we've represented those with just inflow hydrographs with a 1 in 100 year event, effectively. So that's not in relation to sort of the normal conditions the river might be in. That's really just to really force some flow in, just to really test what happens. So we've created our inflow hydrographs, and then we need to set up a polluter graph to set up the baseline PL2 concentration in our river. It's important that we use the same inflow points as the inflow hydrograph. And then we have our setup here. So we've got 2 inflow points, and we're using the same concentration of 10,000 mg per liter. And that is mainly so we can make a direct comparison to our PL1, but we've also used the same concentration. So if we had 50% of one, 50% of the other, we would see equal amounts of the actual volume. We've set the polluter hydrograph up when we were testing it to use the same time step. That's not actually necessary. We looked at it, and you could just set it to a day if you want, if you just want to not have to put in lots of rows of data. But at the end of it, it's still what it is. You just need to have it in. So now we've got our watercourse set up. We've got our 1D, 2D model. We've got our concentration set up. So we want to see what actually happens when we start running this model. So the only thing different to our normal 1D model is that we've included the inflow file and the polluter graph. We've got our existing wastewater profile where we've already set up PL1. And what you do need to do is set up your initial state file for a dry weather flow simulation. And I'm about to show you why you do that through us not doing it. And you can see what the difference is. So you then need to go back to our QM parameters, and we need to make sure that both PL1, PL2 are ticked for this. If you're using an initial state file, the initial state file that you have used has to have both of those ticked as well, regardless of whether you created it with just your 1D runoff. That's because if it doesn't have that, it won't be able to use it. So we looked at our network, and we started running into some issues. When we looked at this section of the network, we noticed we were having a much lower concentration flatlining out, and that's coming out about 6.4 kilograms per meters cubed concentration in our foul combined system. And we found out this was due to base flows being added to the subcatchments upstream. And as base flows don't technically have a sort of a pollutant attached to them, we weren't getting a steady state of 10 in this branch of the system. So this would be a problem if we were looking at sort of just specifically, we want to know wastewater versus pluvial versus fluvial, and we wanted a solid state of 10 for all of them, we would have to think about how else we could represent base flows in our model. This can be done sort of different workarounds, but if you wanted to do it, you'd have to set up as maybe an additional flow, which would then be assigned to a wastewater profile as well. But then you've got to remember that if you've got a diurnal profile that you're using, that it will use the same diurnal profile. So it's something that you've just got to keep an eye on, keep track of everything that you're doing. So now we're looking at our dry weather flow simulation with our watercourse section, and we've got a few different concentration graphs here. And this is just looking at different points in our river. We're flowing south to north. So towards the top of the watercourse, we've got our section which is coming out. It's reaching 10 kilograms per meters cubed quite quickly. As our flow is progressing down the system, we see a slightly later peak up here for our sort of most northern section. And then we're getting some spilling from the watercourse of our river reaches onto the 2D mesh. And we can see when we graph the actual pollution on the 2D mesh, it is just spiking up to 10 kilograms per meters cubed, which is what we want to see. We want to be able to see it coming out at a solid state. We don't want it jumping up at different points. So now we're going to look at quite an extreme event going through the system just to really test it. So we used a 1 in 100 year design simulation. So we've got a lot of flooding in the network, but when you're using something this extreme, that's kind of expected. We're not worried about the amount of flooding, but we are going to sort of try and separate out which bits are flooding, which bits are coming from where. So that's what we're going to look at. So like I said earlier, we have assumed rainfall is clean, which sometimes isn't. We're getting different runoffs and pollutants coming in from our network, but we're not using this at all for sort of a representation of realistic pollutants. We just want to use it as trackers. And we can see our two different concentration graphs here for our different sections of the river. Upstream, we've got less of a surface water contribution going in. So you can see we reach our peak of 10 much quicker. And then our top graph there, you can see because we've got our surface water coming in through the different branches straight into the river, it's diluting the pollutant down quite a lot, and it's taking a much longer time to build up. And that's why you need to set up an initial state, because that would have started at 10 originally, and we would have seen it drop down with our surface water inflows. So it's very much a case of do as I say, not as I do with this example. That's why you don't do it. So now we need to just start looking at our flooding on our 2D mesh. So we've got a few different examples. We've just got this section of flooding along here. I believe it's a road section, so we've got our gully, our curbs containing our flows in there. And we can see if we start graphing for pollutants 1 and 2, we've got 0 concentration in either. So that tells us this is entirely rainfall-driven surface water flooding, and that's shown by those two graphs. We can make a comparison and say, well, 0, 0 equals nothing. We can look at this section up in the top left of the page here. We've got our PL1 coming out at 0.001 kilograms per meters cubed, and 0 PL2. Not surprising, because the river's not actually anywhere near this. I'd be a little bit worried if I was having PL2 coming out here. So we can make an assessment and say, oh, this ratio kind of shows to us that this is 0.01% wastewater flooding mixed in with surface water. And then if we look at another section here, we've got a section of flooding nearby the river, and we're having 0 PL1, 9.4 kilograms per meters cubed of PL2. We can make an assumption this is roughly 94% flooding from fluvial sources mixed in with some of our cleaner surface water that we haven't got a actual pollutant for. So I've been saying that rainwater is clean, but in reality, we do get different sources of pollutant coming in from different points. So we wanted to see if we could assign a pollutant directly to the rainfall to apply to the entirety of the mesh. And we started looking at using non-attached pollutants. So this is again in our water quality parameters. And we want to change the build-up wash-off model from the Innovyze default to the SWIM model. And then we want to set determinant PL3 to have the same concentration of the 10 kilograms per meters cubed we've used previously. We set this up, and we couldn't actually get it to work. So we were just playing around with it, sort of in our spare time, trying to get it to work. Couldn't quite get there. If anyone who's used sort of the water quality modeling has got any tips, please help me. But I can see Andrew nodding away, so hopefully he has some tips for me. But it's something we couldn't quite get to work. We looked through all the help files, couldn't quite get there. But that would be our next steps. So we could then, instead of having our surface water as clean, we could have it as PL3. We could then look at different ratios a lot easier. So just to conclude, it really helps with promoting the partnership work between different stakeholders. And I can quite happily say that as a private consultant. So it's if the water companies and sort of the flooding agencies can get together to sort of better understand their own risks, it really encourages sort of better planning and better results for the customers at the end of the day. And what we have shown is that it can actually help appropriate the responsibility of flooding events a little bit. So we can say, oh, well, we are getting some wastewater flooding, but we're getting river coming in at a later date. And that's when it is quite important to look at the time varying data. So you might see a spike initially of wastewater, but then you'll see a sudden surge of your fluvial flows coming in. And so it's like, well, yeah, it is originally flooding from the manholes, but then we're getting this river overtopping and sort of hiding all the evidence. So it will give us a better understanding of flooding triggers, and we can increase the complexity when needed. So we built up a PL1 model initially, and then we brought in PL2. We want to be able to try and bring in PL3 and just working our way up. And you can just assign it to different flooding triggers, such as tidal or groundwater, if you want. So it's a lot of different potential to use. So we've used our different pollutants as trackers for different flows, and yeah, could not get non-attached pollutants quite to work. So that's me. Thank you very much for listening.